I recently made a video sharing my thoughts about why I think Solomon Nelson's takedown of Mike Israetel's PhD is warranted. Fundamentally, I argue, along with Solomon, that it is a vacuous contribution, or really lack of contribution, to the scholarly community. And I got a lot of good comments, both critical and agreeing with me on my video about my understanding of the PhD and what a PhD should look like. I got questions and critiques like, is a PhD meant to be groundbreaking? Is it sufficient to have a literature review that displays understanding of past research? And isn't it okay to have some small iterative contribution? These are really good questions, and I'm going to attempt to answer them thoughtfully in this video by showing what good PhDs actually look like. I'm going to also address some other questions like, is the problem that Mike went to an uncompetitive school, East Tennessee State University? My answer to that is emphatically no, that is not the issue. I'm going to prove that by talking about 3 good and really great PhD dissertations. One from Stephen Hawking, one from Richard Dawkins, 2 scientists you may know well. And then a third from a really good scholar who did their PhD in biomedical sciences at East Tennessee State University, the same institution Mike went to. I'm going to use this to show that lower tier schools can have great departments in certain areas. Hopefully this drives home a more comprehensive picture of what good PhDs look like. And I think it's helpful to start with some really brief background about what the PhD even is. A PhD is an acronym that stands for Doctor of Philosophy. That does not mean that someone who earns a PhD is a philosopher necessarily, although someone can earn their PhD in philosophy. The reason it's called that is an artifact of the history of the human intellectual tradition. That sounds a little bit snobbish, but it's actually true because philosophy is the most foundational and the oldest organized intellectual discipline. It is the birthplace of all the other disciplines. So for example, science was born out of so-called natural philosophy. Philosophy is the love of wisdom, and it's all about fundamental questions about reality and purpose and exploring the universe around us. So it makes sense that doing a Doctor of Philosophy displays that innate wonder and curiosity about the world. The Doctor of Philosophy degree started in Germany, and I'm actually going to read an excerpt from a nice conference proceeding from a 2018 research conference at the University College London. So this excerpt reads, Wilhelm Humboldt proposed a new type of university based on research and teaching, introducing the idea of Lernfreiheit, that scholars should be free to specialize. As education minister, he was instrumental in the establishment of the University of Berlin, which is now Humboldt University, in 1810. From the start, they introduced a PhD, Doctor of Philosophy, which was based on research and influenced the teaching of the university. Other universities in the German-speaking world soon followed. In France, the Napoleonic reform of higher education also resulted in the introduction of the PhD in 1810. The Netherlands introduced them legally in 1815, and the University of Zurich gave its first in 1833. Yale gave the first PhD in the USA in 1861. The dates of the first research-based PhDs at some of the League of European Research Universities are given in Table 1 below, and Table 1, which I'll show now, shows the dates of the introduction of the PhD at different UK schools. And after Yale introduced the PhD to the USA in 1861, many other American universities followed suit. The whole goal of the PhD since its inception was to train in an apprentice-style mentor-mentee relationship future research scholars in their field. To gain entry into a PhD program, a student needed to show mastery of a broad overview of the relevant scholarship, not just in their specific field, but to be able to have mastery or at least some good competency in science, philosophy, or at least as it was at the time, politics, culture, and then move on to specializing as a researcher in their discipline. And fundamentally, a PhD, since its inception in 1810, has been about training people to be research scholars. So what really does that mean? Well, all good PhD programs share several key elements that make a PhD and really the dissertation a good example of exemplary scholarship. Some of those are responsible conduct of research. You need to be able to responsibly engage with past literature. You will never represent, or rather never misrepresent, past work. You'll never twist things to say something they don't actually mean. You will always act with integrity as a scholar, trying to pursue truth. If you're curious about why I paused to say that, it's really because it's actually much harder to show something to be true than it might seem. Truth is all about corresponding to the way the world actually is. And all scholars try to do this, but it actually ends up being kind of tough. And if you're curious why, I highly recommend watching some crash course philosophy videos on epistemology, the theory of knowledge, because you end up realizing that it's actually very difficult to provide good arguments for the things that we think we know, let alone to know with certainty that something is true. It's very difficult. And just because a piece of scholarship is really good and rigorous doesn't mean everything it says is true. And that's okay. That's just an artifact of it being immensely difficult to prove things. And that we still work within that limitation and engage in responsible conduct of research to do our absolute best to seek truth. Good PhD dissertations also bring conceptual clarity. This means that they understand things enough to be able to explain them in a clear way, and they can combine diverse concepts in a meaningful way to their readers. This is very important. There needs to be a clear command and evaluative synthesis of past research. This is not the same as a descriptive summary of past research. So for example, if I was doing a descriptive summary of some research paper, I would say, oh, first the author said this, then the author said this, and then lastly the author said this, okay? So I'm showing that I read the thing and I can repeat it in maybe a paraphrased way. That is not the same as an evaluative synthesis, where you're thinking about the motivations and the thought structures behind that work. You're engaging with whether the first thing they said makes sense, or if the second thing they said makes some sense, but it would make more sense in light of this extra information, or it actually doesn't make sense in light of this other information. You're engaging with the literature as opposed to just rotely summarizing it in a non-evaluative way. So you need to be able to have a good literature review. You need to engage with the literature, but evaluate it and synthesize it. That is very important. And then another, and probably the most important and most necessary part of a good dissertation, is a novel contribution. This can take many forms. It can either be something groundbreaking or something, more commonly this is the case, incremental and interesting in a new way. So again, it doesn't have to be earth-shattering, groundbreaking work, but it does need to be new and move the field forward in some at least incremental way. And if you're curious what that looks like, there's a really good video that I'm going to show right now and talk about that's all about an animated guide to the PhD. This is from someone named Matt Might. Imagine a circle that contains all human knowledge. We have this small area within the circle that encompasses everything you learn in elementary school. Okay, you know some things, and as you finish high school, you're continually learning a bit more about things. Your knowledge expands. As you get into higher education with a bachelor's degree, you get a major that gives you a little bit more understanding of some specialty with some general education. Master's degree can even deepen that specialty more deeply. And as you start reading research papers, you're getting further to the edge and the boundary of what we know. Then, once you're at that point, you hyper-focus on a specific subtopic, and it can be something gigantic or something small, but it needs to be something that allows you to make a contribution to push the field forward in some way. At this point, you've spent several years thinking deeply about this specific subtopic, but you've already spent enough time to be able to make a novel contribution that ends up moving the field forward. And that little blip on this whole sphere or this whole circle of human knowledge is a PhD. That's really what it's all about. Having some new insight that moves the field forward in at least an incremental way. And if you're curious what that looks like, because that can sound a little bit abstract, there's actually a number of different ways that someone can do this, and they can combine these ways, but it needs to have at least one of these. It can be an objection to something. Maybe there's some idea out there that's really popular. A whole PhD dissertation can literally be objecting to that idea, and you really want to hyper-focus on some specific topic and then bring all you can bear in terms of evidence, data, to show why that specific idea doesn't work. That's a contribution because it's already moving the field forward and showing, okay, maybe this idea that we take to be true isn't the best way of representing this knowledge structure. Okay, that's one valid option. Another is to defend an established idea in light of some new objection. Let's say there's this idea that's pretty popular in your field, and there comes this new objection from some other field or from some really prolific scholar in that field. You might want to defend this idea in light of this objection. That's a new contribution because you're showing, hey, this idea that we take to be true still holds up, even in the face of criticism. That's super valid. You can also test a new hypothesis. Maybe as you're reading the literature on a topic, you're like, oh, you know what, there is this idea I have that maybe this is the way this specific system works. You can go out and test it. And even if your hypothesis fails to actualize and you aren't able to show that what you thought might be true is true, that's still a contribution because you put the effort into testing that hypothesis. And then even if it doesn't end up being true, you still showed, hey, I put a lot of rigorous effort into this. And this negative result is still new knowledge to us because it shows that at least this hypothesis is not the way things are. That's valid. You also can revise an already established hypothesis. Maybe you want to change one aspect of some commonly held view. You can absolutely do that. And that is another way of having a real contribution. And then this is going to be most appropriate to this dialogue specifically. It's actually valid to have your dissertation be a confirmation of an established idea as long as you have a new methodology, you have some new way of showing that this is true based on some really new information or a new methodological approach to thinking about things, okay? So it can literally be confirmatory as long as there's some novel thing in the way that you're showing that established view to be true. Finally, you can have a really meaningful contribution if you think about some new theoretical structure or a new paradigm to be able to take another look at the past data and show how it maybe makes sense in a totally new theoretical structure. That's super valuable, and that's something that historian of science Thomas Kuhn has called paradigm shift, which is really cool. These are all different options, and after someone writes their dissertation, well, at least in the US, PhD paper is called dissertation. In Europe, it's called a thesis. So once they write that PhD paper, after that they defend it in front of a committee because the whole idea is that you need to be trained as a scholar. So the end result is not just writing a paper that contributes something new, it's being able to defend it as a valuable piece of work in front of the scholarly community. So all good PhD programs require not just writing the dissertation or thesis, but defending it in front of a committee. Your committee involves people who are experts, at least at good institutions, these are experts in the field. So your research mentor, otherwise called your principal investigator. Usually there's a few other faculty who are committee members that are going to be asking you tough questions, grilling you about your dissertation. Why did you use this method? What do you think your work contributes to our field? Tough questions. Usually these can be anywhere from an hour to even 3 hours or potentially longer, times where you're literally just standing, being grilled about your dissertation, and you have to be able to defend it as a scholarly contribution. So these are all necessary parts of a good PhD dissertation or thesis. Fundamentally, I think I've argued that Mike Israetel's PhD does not meet these criteria. I think Solomon Nelson outlines the case really well. I want to show a little bit super briefly why I think his fails and contrast it with 3 great dissertations that definitely meet this criteria. So we're going to go ahead and get into the first one, which is Stephen Hawking's PhD thesis. For this section, I'm going to do a few things. I'm going to first read the abstract for each dissertation, because I think that, although it may be, a slower part of the video, I think it's actually super important to know what a real good scholarly contribution looks like at the PhD level. And if you're curious about my academic background to be able to evaluate things like this, let me first, before I list my academic qualifications, say that me, like everyone else on the internet, are people. I think we're all rational people, or at least we have rational faculties that we can develop to be able to think better about things. Ultimately, just because I or anyone else have academic qualifications or no academic qualifications does not mean that the things we say are true. The best way to critically evaluate whether the things that me and other people are saying are true is to actually do your own thinking about these things by looking at the primary sources. So I'm going to talk about 3 dissertations. I'm going to link them below. I highly recommend anyone who's curious to dig deeper into this to actually look at those papers yourself, because I can say whatever, right? But looking at them yourself is a good way to think about the actual contribution and the thought processes. You can evaluate whether you think they're good or not. Even if you don't have training in these fields, you can at least read them and take away, okay, is this engaging with past literature or just summarizing things? Does it look like it's actually doing something new? And what does the author claim that their paper is doing? My qualifications, I have undergraduate degrees in biology, philosophy, computer science. I have graduate training in biology, philosophy, and computer science. And I am a previous adjunct professor of biology. I am, in the next few months, applying to MD, PhD programs where I will be doing a Doctor of Medicine and a Doctor of Philosophy. I have some experience with graduate coursework in physics and philosophy of physics as well, so I have some background to be able to evaluate Stephen Hawking's dissertation thesis, even though it's not in my field right now. Properties of expanding universes. Stephen W. Hawking. Thesis presented for the degree of Doctor of Philosophy in Theoretical Physics and Applied Mathematics at the University of Cambridge. Some implications and consequences of the expansion of the universe are examined. In Chapter 1, it is shown that this expansion creates grave difficulties for the Hoyle-Narlikar theory of gravitation. Chapter 2 deals with perturbations of an expanding homogeneous and isotropic universe. The conclusion is reached that galaxies cannot be formed as a result of the growth of perturbations that were initially small. The propagation and absorption of gravitational radiation is also investigated in this approximation. In Chapter 3, gravitational radiation in an expanding universe is examined by a method of asymptotic expansions. The peeling off behavior and the asymptotic group are derived. Chapter 4 deals with the occurrence of singularities in cosmological models. It is shown that a singularity is inevitable provided that certain very general conditions are satisfied. Now, you may be watching this video as a non-physicist, and you may be a bit confused as to what this really means. But even if you're a non-physicist, you can critically examine this abstract and ask yourself questions like, does it seem to be engaging with past literature? Does it seem to be moving the field of theoretical physics forward in some way? And even without reading the rest of the dissertation, we can answer both of those questions and others with a resounding yes. In terms of engagement with past literature, we see that Chapter 1 Hawking is engaging directly with a previously argued view of the theory of gravitation from Hoyle and Narlikar, and showing that the expansion creates difficulties for this view. And this alone is already a novel contribution because it's objecting to a view by bringing in new information. That already meets one of the criteria that we talked about for a good PhD. This isn't the whole of the PhD though. So chapter 2 is dealing with how do we account for the existence of galaxies in an expanding universe. In chapter 3, we also see an engagement with past literature. We see this reference to peeling off behavior, which is not necessarily Hawking's original idea. The whole point is to engage with this previously published idea and show its consequences for an expanding universe. And then in chapter 4, we have arguably the most important part of this paper, which is arguing that a singularity is necessary to explain an expanding universe. For a long time, people thought the universe was infinite. And then once it seemed pretty clear that the universe was expanding, the question arose, how do we make sense of an expanding universe? There were different ideas like the steady state model, the oscillating model. Maybe the universe really is infinite, but it appears like it has a finite lifespan because it oscillates from dense to more dense and less dense. And then there's also the Big Bang model, which is the idea that the universe started with a singularity and then expanded from there a finite time ago. And Hawking's work provides evidence in favor of the Big Bang model in cosmology. Just taking a brief look at some of the mathematics here, we can see so much intellectual contribution here. There really is a ton of work that Hawking has done throughout this to argue in favor of his position. And even if Hawking were wrong about some things, the whole point is to do your best to argue for a position and do so with a novel contribution to the field. That alone is the whole idea of the PhD, and that's what makes Hawking's PhD so great. C. Richard Dawkins, Selective Pecking in the Domestic Chick. Balliol College, Oxford, thesis submitted for the degree of Doctor of Philosophy in Zoology. When a chick pecks at one of a number of alternative stimuli, two questions about mechanisms of decision-making arise. One of these concerns the timing of the peck. This will be discussed later. And the other is about its orientation. In an attempt to answer the second of these questions, a model is proposed called the threshold model. This model then is a possible analog of the mechanism in a chick which determines at which of the available stimuli each individual peck is directed. The threshold model embodies the following assumptions. There is a fluctuating variable of unknown nature called variable x, which interacts with thresholds corresponding to the external stimuli. A stimulus cannot be pecked unless variable x exceeds its threshold. Some stimuli have lower thresholds than others and are therefore more likely to be pecked. They are preferred. If the thresholds of more than one available stimulus are exceeded at any one time, they are equally likely to be pecked. And it goes on. We can see immediately in this excerpt of the abstract, Dawkins is doing a few things that are new, including the proposal of a new model called the threshold model, which is all about behavior and animal choice. How does an animal choose to take one action versus the other? The model system here is the domestic chick. We can see Dawkins is also engaging with the past literature, citing other models, other examples, and his colleagues' data as well, which is totally part of the whole evaluative synthesis of past research goal of a good PhD research paper. We also see some engagement with potential other models like the go-no-go model. And Dawkins in the abstract also talks about some areas that he would like to test or could be tested in the future, suggesting future research directions. Dawkins has defended his model pretty well. And again, even if the model is not the best way to represent the way animal choice works, this is still a well-argued dissertation. It's still a thesis that's doing its best to have responsible conduct of research, proposing something new that actually is a contribution to the scholarly community. And further work can either confirm it or show it to be not the best explanation of animal behavior. Avinash Thirumalai, Regulation of C-reactive protein gene expression and function. A dissertation presented to the faculty of the Department of Biomedical Sciences, East Tennessee State University, in partial fulfillment of the requirements for the degree Doctor of Philosophy in Biomedical Sciences. Human C-reactive protein, CRP, is the prototypic acute phase protein whose serum concentration increases rapidly during inflammation. CRP is also associated with atherosclerosis. It is deposited at lesion sites where it may interact with modified lipoproteins. There are two major questions regarding CRP. 1. How is the serum concentration of CRP regulated? 2. What are the functions of CRP in atherosclerosis? Our first aim was to determine the role of this constitutively expressed transcription factor OCT1 in regulating CRP gene expression. We found that OCT1 overexpression inhibited IL-6 plus IL-1 beta induced CRP gene expression. Maximal inhibition required the binding of OCT1 to an octamer motif at -59 to -66 on the CRP promoter. OCT1 overexpression inhibited both IL-6 plus IL-1 beta induced EBP beta induced CRP gene expression even when the OCT1 site was deleted. These findings suggest that OCT1 is a repressor of the CRP gene expression that acts via binding to its cognate site on the CRP promoter, as well as through indirect interactions with other promoter-bound transcription factors. Our second aim was to investigate the interaction of CRP with oxidized low-density lipoprotein, OX-LDL. Acidic pH, a hallmark of atherosclerosis lesions. Acidic pH, a hallmark of atherosclerotic lesions, reversibly alters CRP structure and exposes a hidden binding site that enables CRP to bind OX-LDL. Using site-directed mutagenesis, we constructed a CRP mutant, which is E42-Q. This is identical to glutamine mutation at location 42 that showed significant binding to OX-LDL at physiological pH. E42Q CRP required a less acidic pH for maximal binding and bound OX-LDL more efficiently than wild-type CRP at any pH. We then examined if reactive oxygen species also induce CRP-OX-LDL interaction. H2O2 treated CRP-bound OX-LDL at physiological pH. Like acidic pH, H2O2 treatment induced only a local structural change, exposing the OX-LDL binding site. E42Q and H2O2 modified CRP are tools to study the function of CRP in animal models of atherosclerosis, which may not have an inflammatory environment sufficient to modify CRP and induce binding to atherogenic OX-LDL. We conclude that OCT1 is one of the critical regulators of CRP gene expression, and that CRP can be modified in vitro to convert it into atherogenic LDL binding molecule. Here in the abstract, we see Thirumalai signaling a few novel contributions to the whole field. We have these two research questions: how is the serum of CRP regulated, and what are the functions of CRP in atherosclerosis? And this dissertation doesn't have to answer both of those questions exhaustively. Even answering small parts of this question help a lot. And we can see the thought process here where he and his team are thinking, okay, how do we think about the regulation of CRP? Well, maybe we want to start by looking at the genetic level and thinking about the biochemistry involved with different transcription factors, things like that. And they end up looking at OCT1 as a candidate for the regulation of CRP gene expression. And they found something new in their study, which is that OCT1 is a repressor of CRP gene expression. That alone, we can see, is a new thing. All of human knowledge did not know that before this paper. Boom. Okay, literally something new. Boom. That's already a novel contribution. And then we see other work that's also adding to this whole picture of trying to understand the CRP gene and atherosclerosis. And we have more work here that's being done towards that. And the conclusion summarizes nicely what the contribution of this dissertation is. So Thirumaalai says, we conclude that OCT1 is one of the critical regulators of CRP gene expression, and that CRP can be modified in vitro to convert it into an atherogenic LDL binding molecule. So we have at least two big things. One is, again, showing that OCT1 is a repressor of the CRP gene, and showing that CRP, the protein itself, can be modified so it ends up being a low density lipoprotein binding molecule. Those are at least two genuinely new things that no one knew before this paper. And that is awesome. Even if people had some hint that those things might be true, this dissertation is showing that to be true. And you can just look through the paper and look at all the experiments that they did for little parts of each of these contributions. And it's very clear, even to a non-biologist, that there is some actual data here. It looks like there's evaluative synthesis of past work and some actual new findings here. And again, this is someone from East Tennessee State University, the same institution that Mike Israetel earned his PhD from. And this is just going to show that even at the same institution, there can be different quality and different standards of academic rigor. At the best institutions, all the departments are generally going to have really good academic standards. But I really wanted to highlight Dr. Thirumaalai's dissertation because I really want to show that it's not like East Tennessee State University is inherently scholarly bankrupt. Like, it actually has some good scholarship going on there. And this dissertation is a really good case in point. So what can we learn from these three dissertations? Well, the scope of the study system can vary widely for it to be a great contribution. With Hawking is literally dealing with the origin of everything, right? The origin of the universe. How do we make sense of an expanding universe? And then on the flip side, Thirumaalai is dealing with tiny things that are not subatomic, but submicroscopic, where we're looking at proteins and individual genetic structures that are on a very small scale. And even though the scale is different and the grandiose nature of the questions can be different, they're both great contributions that are moving their fields forward. And in the case of Dawkins, his abstract might read like a bit of a just monotonous everyday thing. Like, oh, I'm looking at how birds choose to peck things, right? But that even is helpful in trying to understand animal behavior and the choices that animals make. So all three of these dissertations are providing some new information. Arguably, Hawking's was groundbreaking, combining brilliant insights into something that is actually potentially going to change a whole field, right? Dawkins and Thirumaalai's papers are less groundbreaking in the sense of totally doing a paradigm shift in the field, but they're still really valuable because they are incremental contributions that are new contributions that are evaluatively synthesizing past research and proposing some new ideas. So these three dissertations, I think, do a great job of illustrating the range of grandioseness to just everyday incremental things that are still valuable to the scholarly community. In comparison, we can look at the final draft of Mike Israetel's paper and show why, even from the abstract, we have signals that this is not a strong contribution to the scholarly literature. So I'll go ahead and read the abstract, which is the final version that Mike's friend Milo posted on his YouTube channel. So let me go ahead and read this one. The purpose of this dissertation was to explore the interrelationships of several important fitness characteristics in Division I athletes. Sport performance magnitude is the summation of an individual's athletes' technical, psychological, and fitness characteristics. Athletes that excel in any or all characteristics perform better in their chosen sports. General fitness characteristics that are important to almost all sports include strength, power, vertical jump height, short distance sprinting ability, muscularity, and body fat percentage. These variables have been shown in previous research to independently affect athletic performance outcomes, but their relationships to one another are less clear. 88 Division I athletes from 4 sports were examined in a variety of fitness characteristics as part of a continuous athlete monitoring program. Data on strength, power, vertical jump height, short distance sprinting speed, muscularity, and body fat percentage were collected and analyzed. Analysis revealed several important relationships. Firstly, strength is highly related to muscularity, with lean body mass as one of the most important determinants of strength. Secondly, athletes that can produce high relative scaled per body mass forces and powers tend to be much higher jumpers and much faster sprinters. Lastly, leaner athletes outperform less lean athletes in almost every metric, especially relative strength and power, vertical jumping ability, and sprinting ability. We can ask ourselves, are we seeing the same signals of a great PhD thesis in this abstract? Are we seeing an evaluative synthesis of past research? Well, there is some signaling that Israetel is engaging with past research. Israetel mentions that previous research has been shown that these variables affect athletic performance, okay? So the question is, what is Israetel's contribution here? Well, we can see it signaled here at the bottom. Strength is highly related to muscularity. Athletes can produce higher relative forces if they are, or rather, athletes who can perform higher relative forces are better jumpers, faster sprinters. And third, leaner athletes have better jumping ability and athletic ability. So the question is, are these even incremental insights? And the answer is no. As early as the 1970s, we knew that increased muscle mass increases strength, increased force output, meaning increased power, enables higher jumping, higher sprinting speed, and that having a body composition that's leaner is more amenable to athleticism. And if you're curious what my sources are for this, I would actually direct you straight to Israetel's dissertation. So on page 26, he says, muscle is the direct producer of force. Larger cross-sectional area almost always results in a higher ability to produce force. And this includes citations going back to 1970. Muscles with a larger anatomical, physiological cross-sectional area are able to produce greater force when maximally activated. It is not unreasonable to assert that the cross-sectional area of muscle, particularly type 2 fibers, is the most important absolute contributing factor to strength production among similarly trained athletes. And we have some other citations within the dissertation that further confirm this. So on pages 32 to 33, Israetel says, many of the advantages of increased strength, the ability to produce force on sport performance, are expressed through the effect of strength on power. Power, which is the product of force and velocity, or the product of strength and speed, includes the ability to express force at high velocities. Greater force-producing capabilities can produce higher powers and velocities of movement. Improvement in power and velocities especially impact the potential for enhanced sport for performance, with citations going back to 1995 on that one. So we see a recognition by Israetel that the findings that his whole dissertation is about are well established, going back as early as the 1970s, with further confirmation in the 90s, 2010s, throughout this whole decades-long time. So the question is Israetel's paper novel in any of the ways that we talked about? We can go back to that list to remind ourselves what we're looking for. Things like incremental or groundbreaking. It can be either. It doesn't have to be groundbreaking. An objection to something. Defense of something in light of some new objection. Test of a new hypothesis. Revision of an already established hypothesis. confirmation of an established view with new methods, with new insights, or a new theoretical or interpretive paradigm. There's no objection to an established view, okay? Is it a defense of something in light of some new objection? Well, it is defending something, but not in light of some new objection. Is it a test of a new hypothesis? No, this is an already established hypothesis. Is it a revision of an already established hypothesis? Nope, already established. And then this is the one that a lot of people argue for. Is it a confirmation of an established hypothesis with new methods, with new data, with new insights? The answer is a resounding no. There is no new method here to further confirm a long established hypothesis that, again, literally reading his abstract, strength is highly related to muscularity. We knew that. Well, we had really good data on that as early as the 1970s, according to Mike's paper. Is, the ability of an athlete to jump higher and sprint faster related to their force production? Yes, we knew that. Same time. And then third, can leaner athletes outperform less lean athletes? Yes, we knew that since the Olympians in Greek times. So there is no new method to test these. And if you're curious what proof I have for that, the proof is in Israetel's dissertation itself. If you go through it, you see an adoption of previous methods that are well established to further establish this already decades-long established set of ideas. So is there any even incremental contribution? No, there's no incremental contribution. This is not even an evaluative synthesis of past work. It's just a description of past work with no engagement of the idea. So that is why Israetel's PhD thesis is not a good one, whereas the three that we talked about are really great ones. So what are some takeaways that we can learn from this? Well, one, good scholarship matters, and you can get good training at a lot of different schools that will give you the traditional PhD scholarship training in terms of making a novel contribution. The whole idea is not to just superficially summarize past work. It's to engage with it, evaluate it, and again, make a new contribution, which does not have to be groundbreaking. It can be incremental and still be excellent, as we saw. The school that you go to does matter, and prestigious schools tend to have good departments all around. But even lower ranked schools like East Tennessee State University can have really good departments. Based on the dissertation we looked at, their department in biomedical sciences genuinely is good. They produce good PhD researchers. Fantastic. Viewers might be surprised to hear the names of universities that are the number one in their fields. For example, if you want to study entomology, which is the scientific study of insects and other arthropods like millipedes, spiders, the best place in the world to do that is not Harvard, it's not Oxford, it's actually the University of Florida. And if you're curious what reasons I have for thinking that, my first master's was a fully funded master's in entomology at Washington State University, which has a really strong agricultural entomology program. Even we knew, though, that University of Florida always has the best of the best. It's virtually the oldest program, and it has just so many resources for studying bugs. On the other hand, if you want to study philosophy, the best place in the world to do it is not Stanford or MIT, although they're obviously world class. It's actually New York University. Don't take my word for it. This is coming straight from the Philosophical Gourmet Report, which is a database where current philosophy professors rank other universities and say what they think is the best. And New York University beats out Oxford, Stanford, Harvard, consistently year over year. In the United States, if you want to study history of science, one of the best places to do that is the University of Oklahoma, which is a little bit random, but that hopefully just goes to show that even at schools that aren't the Ivy League or the oldest or the best in the world in all domains still can have some good research output. So all this to say, hopefully this has given some insight about what a PhD is, what good PhD dissertations look like, and what bad ones should strive to be like. I'm happy to answer any questions. Hope this is helpful, and thanks for watching.